Specific speed can tell you whether a duty point leans toward centrifugal, mixed flow, or axial architecture, but it cannot pick the final fan. The useful question is not, which fan has the biggest number? It is, for this required flow and pressure, what rotor family is geometrically comfortable? We will build that screening coordinate, expose the convention traps, and then show the checks that still remain. Start by freezing the duty point. Record volume flow Q, the declared fan pressure rise delta P, gas density ρ, and rotational speed. State whether the pressure is static or total and whether speed is revolutions per minute or angular speed. Specific speed evaluated at one arbitrary curve point is not the design fingerprint usually intended. Compare machines at a consistent reference, commonly near their best efficiency region. One common dimensional form is n sub s equals north times the square root of q, divided by delta p to the 3/4 power. That number inherits the chosen units. Change cubic meters per second to CFM, pascals to inches of water, or RPM to another speed basis, and the numeric value changes. Some references use head instead of pressure and add a coefficient. Never copy a boundary without copying its complete convention. A dimensionless form removes that unit dependence, omega equals angular speed omega times square root q, divided by delta p over rho, raised to the 3/4 power. Omega needs radians per second, cubic meters per second, pascals, and kilograms per cubic meter in one consistent psi calculation. Dimensional n sub s and dimensionless omega are related ideas, not interchangeable numbers. Label the symbol and convention on every chart. Why does the coordinate work? Similar fans obey the familiar scaling pattern: flow follows speed in size, while pressure rise follows speed squared in size squared. Combining the required flow and pressure with speed collapses much of the scale information. The result describes the balance between volume handling and pressure generation that the rotor geometry must support. It narrows a family, it does not replace a performance map. Read the spectrum as a tendency, not three fenced boxes. Lower specific speed means comparatively more pressure duty and less flow duty, which generally favors radial or centrifugal turning. As the coordinate rises, mixed flow geometry shares radial and axial work. At the higher end, axial geometry becomes natural for comparatively large flow and lower pressure rise. Exact transition bands depend on the definition and design database. At the lower side, a centrifugal wheel accepts air near the axis and turns it outward. That radial change in momentum and the downstream diffuser or housing support pressure generation. The real backward curved wheel here proves the physical form, not a universal cutoff. Blade loading, inlet geometry, width, diameter, speed, housing, and duty points still determine whether a particular model is a sound selection. Mixed flow geometry occupies the transition, sending the stream both outward and downstream. It can combine more pressure capability than a simple propeller with a straighter flow path than a conventional radial machine. The current mixed flow catalog page provides visible construction context only. Our animated velocity triangles explain the idea. Neither image nor animation establishes an industry-wide numeric boundary. At the higher side, an axial rotor moves most of the stream along the shaft direction. That architecture is comfortable when volume dominates over pressure rise, but axial does not automatically mean low performance or high efficiency. Hub ratio, blade section, tip clearance, guide vanes, casing, stall margin, and system resistance matter. The real AC 800 footage is shape evidence, not a curve or rating claim. Here is a convention-safe comparison. Hold speed, density, pressure definition, and units fixed. Duty A has relative flow 1 and relative pressure 4. Duty B has relative flow 4 and relative pressure 1. In n square root q over pressure to the 3/4 power, A scores about 0.354 and B scores 2. B is therefore about 5.7 times higher on the same screening coordinate without inventing an absolute family cutoff. Specific speed still cannot choose the exact fan. Now open the manufacturer curves and verify the operating point, stable range, efficiency, absorbed power, motor margin, sound, temperature and density corrections. Then check size, inlet and outlet constraints, guards, filters, elbows, contamination, materials, bearings, control range and maintenance access. System effect can move the installed duty far from the catalog point. Use a 4-step release workflow. First, lock Q, pressure definition, density, speed basis and units. Second, compute one clearly labeled specific speed convention. Third, use it to shortlist centrifugal, mixed flow or axial candidates. Fourth, verify each exact model on tested curves and the installed system boundary. Specific speed is a powerful map coordinate. Engineering selection begins, rather than ends, at that coordinate.